Hello everybody, welcome to this course on linear systems theory. This would be for a kind of an introduction to any advanced level courses in systems and control theory. Of course, there would be several others which could go in parallel, but to start off, I think linear systems theory is a nice gateway to expose yourself to courses on, say, hybrid systems or nonlinear systems, geometry control, optimal control, and so on. So one of the basic things in engineering is to equip ourselves with the right kind of tools for analysis and design purposes. So if I just talk of engineering tools, something that would outright come to your mind is something like this, right, across domains, and that is what we are trained to be as engineers, or that was what was in our mind when we were as kids aspiring to be engineers. So one of the important tools which we don't really think of, or which we are introduced to much earlier in life, is on the tools of mathematics. So just to begin with, I'll just quote something from a very nice article which you can just read from this link, is on teaching mathematics of so this is by one of the very famous mathematical physicists of our times, called V.I. Arnold, and what he says is that maths is a part of physics, right, and physics is a experimental science, a part of natural science. So if you look at all romanticized versions of inventions or discovery which we learn through our school training, could be the Newton's apple or the Archimedes principle, or somebody discovering something via an accidental experiment in a garage, was all results of some experiments or some observations from nature, right. So therefore he says physics is an experimental science and a part of natural science. Okay, where does mathematics fit into all these things, right? So what he says later on is that mathematics is a part of physics where experiments are cheap. Okay, we have done a lot of these experiments without realizing that we are using mathematics as a tool of experiment. So if you are an electrical engineering, so in one of the earlier courses on machines, you would do, for example, an equivalent circuit of a transformer. Okay, why is that important, right? So we never ask ourselves that question, but but we are trained to solve problems, go to the exam hall, solve those problems, finish our course and go back. But the equivalent circuit of a transformer is powerful in itself, right. So once I get the equivalent circuit parameters, the circuit model, then I can run whatever experiments just by using standard circuit theory. For example, what could be the efficiency of a transformer which is operating on a load of a power factor 0.6 and blah blah blah, right. So all those things, I don't really need to buy a transformer, run through experiments and get my result, right. Then I have to do a million experiments, and it is very likely that I might end up damaging the equipment. So the power of math here, or what I am trying to introduce you through this course, at least in the initial part, is the power of mathematics in understanding dynamics of a system, and also to develop tools for analysis and design purposes. Okay, so just to begin with, I will just say that one of our ideas would be to just get the physics right, and rest is all mathematics. So the tools from math are as important as what you see in the slides, say for example here, or maybe they are in some sense more powerful. Okay, so before we go into designing any system, or designing, since we are in a control course, so we think that most of the times the objective is to give me a plant and I will design a controller, say a rocket launcher or a automotive device or a process plant and much of that. But before we do any of those techniques of control, we first need to understand what the system is about, right? And therefore, we will spend a good amount of time during this lecture just looking at some basic models, not really advanced models like rocket launcher or a Segway scooter or any things like that. We will just keep things simple, that we could slowly have a transition from what we learned in our undergrad course, or even from bits and pieces from high school physics to develop a general theory or a general framework for understanding systems. So, and much of these things which we in control borrow are tools from theoretical physics, especially related to dynamical systems. So, a bunch of textbooks or literature is available on the theory of dynamical systems, ranging from ordinary differential equations to chaotic theory and so on, which are many of them are now also some kind of popular books. Say for example, the book on chaos theory, for example, right. So, we start by just looking at, okay, of understanding, or what is the basic question of modeling. Like physicists spend lot of time just understanding systems and developing models. Say it dates back to as long or as back as, say, Kepler's laws, which were models built by lots of observations just to understand, say, planetary motion. And everything in physics, or much of the things in physics, were just models built by observing stuff. Okay, so in our context, so what are we interested in, right? So first thing is, what is a model? Model could be several things, right? So in our day-to-day life, we spend lot of our effort doing models of systems. Say I am interviewing you for a particular position, academically or otherwise. So what I am essentially trying to do by asking you a set of questions, say you are into aspiring to get a job in PSU, you write your GATE exam, get a score, you go to the interview hall, they dump on you a bunch of questions, and then they decide whether to offer you a job or not. So the GATE exam tells me something about you, right, that you are actually a pretty well trained engineer who could crack a national level exam. The questions will help me decide on several other factors, maybe your communication skills, your speed of thinking, and so on. So based on these test signals which I give you right from the GATE exam till your maybe a technical interview or an HR interview, I just build a model of yourself, and this model will help me judge whether or not you can handle problems which are in the real world while you actually go to work. Or do you have enough training or enough tools, or are you equipped or capable enough that I can train you on handling those tools of the industry. So that is a very basic modeling thing which happens. So and that happens, maybe if I want to buy a cell phone, then you have constraints on the price, you have constraints on maybe the brand, and so on. So all we do is we arrive at a conclusion by throwing up certain questions and getting certain answers, right. So modeling is something which we do every time before we even start the actual objective, in this course maybe to design a controller, so to speak. Okay, so in our course, what will these models look like? So these models are mathematical representations to help us understand dynamical behavior of the system, right. So say things, if I again recall the Newton's laws, for example, is well, the rate of change of momentum is force. Or in the planetary motion, they talk of the orbits spanning equal areas in equal intervals of time, and so on. Okay. So again, so this model should be able to describe the behavior of a physical process. A very good example is I just switch off the fan, and how long would it take before it comes to a complete halt? Not only that, so can I predict response of a system to certain inputs? Like in the case of an interview, can I, based on the model, can I predict will you be able to handle a certain job in the real plant? Or for example, the effect of GST on economy, which a little controversial, we still do not know, we still may have to wait to see what are the long term implications of that. In some cases, it could also happen that in the initial phase, or when you inject an input to the system, you might actually see a negative effect. We will also talk of that. These are essentially related to what we call as right-half zeros or non-minimal phase behavior. So the effects are not instantaneous. So therefore, it is important for us also to look at the initial response of the system till the steady state, how the evolution actually happens, right. Okay, what is a good model, right? Again, A good model depends a lot on what we want, or what are the questions, or what we want to do with the model, right. So, what is the purpose? So, if I am interviewing for you for a job in say BHEL, I do not really need to know maybe who your favorite cricketer is, or what your favorite restaurant is, right. It doesn't matter. Those questions might matter in some other modeling, maybe on a dating website possibly those things would matter, right. Okay. So, the model should incorporate all the factors that govern the evolution of a system. So, take a physical model, say I am modeling a car. I need to know lots of things about the car, say for example, maybe a basic model of F equal to ma kind of model, till the models of the wheels, the friction, the engine, and much more, right, of even the fuel injection and so on. Or if I am looking at an electric vehicle, how well I model the electrical energy to the mechanical energy domain. Okay, now is a model unique? Well, each system can be represented by different, not each system, but in a lot of cases the same system can have different models. I will run you through a bit of examples later in the lecture, but it could start with, well, a very basic thing of what we do in electrical sciences from our say 101 course on circuits till electromagnetics. You look at, say for example, a transmission line can have a T model or a Z model based on what is the objective of the model over there. It can also be modeled as a distributed parameter system, right, which you can model delays, reflections in lines and so on, if you vaguely remember what happened in those courses. We will touch upon these examples as we go through the course. Okay, now how do these models, or what kind of models are we comfortable working with, right. So, it should the abstraction of the model. So, again what I will try to write in terms of models may not be the true models, but they are okay, they are good enough to help me predict the behavior of the system. So, it's all what we call as an abstraction of the system. So, a certain differential equation is an abstraction of a system. It is not the exact system, just that I just establish an equivalence between a car and a certain differential equation or a transfer function, for example. So, this is much, so the abstraction should be compact as opposed to a rule based formulation, say maybe which was possibly from computer science, people used to use these kind of models, that if this happens then something like this would hold true, something else happens. We can't really have a set of exhaustive list of rules for a modeling purpose, right. So, we want it to be compact and descriptive enough. Now, how accurate the model should be, it all again depends on what I really want to do with the system, or what is my analysis point. Should I really capture all the small components of the system, or should I just look at the bigger picture, which will just be enough to tell me the immediate behavior of the system. So, some of these questions we will slowly touch upon, and we will not really jump into abstraction as yet, but we will slowly start building this abstraction with the help of certain physical examples which we would already know. Okay, so if you are an electrical engineer, so I'll just touch you through a couple of elements, and then the rest will follow, right. So, if I look at the inductance, right, as an element, what do I know about it? That it's an energy storing element, right. It stores energy in a magnetic field, and as a certain current flows through it, it generates some flux, and I know that the voltage induced is the rate of the flux, or voltage is proportional to di by dt. This is what I know, right, or which I would deduce by some amount of experiments. Okay, so the energy stored, well, we know this too, right. So, okay, what do I learn if I say what is the energy stored in inductor? If we remember by heart, we will say, oh, energy is half Li square, or we also know, we will just directly write this expression as V equal to some L di by dt. But is this completely true? Well, the answer is, well, it is true in a certain operating region where the flux and the current are related through a linear relation, right. we are then ignoring the saturation effects which depends on the magnetic material and so on. So, if I just derive by the standard principles, I would derive the energy to be phi square by L in the linear case. Again, phi is my basic parameter or basic quantity here which defines my system, and this has a direct relation because of this linear relation of half Li square. So, this is where it comes from, right. So, this is the first principle here is just this one and this one. So, what we see as half Li square or L di by dt are very specific cases of that, where the flux and the current are like related linearly. Okay. So, similarly with capacitors, resistors and so on. So, all we learn in our circuits course are things essentially restricted to the linear systems, and we know that they are valid over a large range of operating conditions. So, we are happy doing this just this half Li square. So, how accurate the model should be? Well, all my circuit design I am just happy with this kind of description in a linear setting. Similarly, right. So, if I look at a mass element, right. So, I take a mass m moving in a certain direction. So, what I know is again if I ask you what is the kinetic energy, an obvious thing would be to remember half mv square. Okay, where does this come from? So, in the non-relativistic sense, I know that momentum and mass are related this way, right. And what does Newton's second law tell me? That it is not F equal to ma, right. So, that is what we kind of tend to interpret or say directly that okay, F equal to ma is Newton's second law, but what Newton tells me is the rate of change of momentum. F equal to ma is a special case of that. So, if I look at the work done, then I look at force times displacement, high school physics, and I can write it this way, right. dp by dx, I know that dx by dt is the velocity because of the standard definitions, and then velocity and momentum are related this way, and I get this expression. Okay. Now, and then I can derive the kinetic energy to be p square by 2m, right, and this is also half mv square of what I learned because of the linear relationship between the momentum and the velocity. Okay. So, what does this mean, right? So, when I say well how accurate the model should be, so much of the times when I say half mv square, I am just approximating, or I am just working in a region which looks like this, or in the here maybe I am just operating here, right. But if I see the relation where in a relativistic sense, the relation between the momentum and the velocity, well it takes some other form, right. It depends on c, and much of the realistic velocities which we work are much lesser than c, and therefore, I am happy with a linear approximation, right. So, how accurate the model should be, well depends on on which region I am operating or what I really want to do with the models, right. So, I do not need to really memorize this formula, because in any practical case which I would be dealing with as an engineer, I would not go closer to the speed of light. So, I kind of am happy here, therefore, half mv square is good enough for what all we learn. And of course, physicists call this, so this side of the energy as the kinetic energy and this side as the kinetic co-energy or the co-kinetic energy. Okay, we will not go into the details of that. I can later in the course refer you to a beautiful article which kind of exposes you to all these basic energy based frameworks. Okay. So, let us do some very basic examples which you definitely would have done even in other control related courses. So, one of the simplest example is of any mechanical system which will have a kinetic energy element, which will have a potential energy element, say a spring and some kind of friction in the system, and any mechanical system typically can be modeled in this way, right. So, m is a certain mass, k is a spring constant, d is a damping coefficient, and we are not looking at any external forces. I am just looking at a plain autonomous system with x being my position, x dot the velocity, and x double dot the acceleration, and applying basic Newton's laws would tell me that these are the dynamics of the system. We can also derive this by from a purely physics point of view from the Lagrangian equations or the Hamiltonian equations of motion. Okay. So, I can write these equations also in the following form, right. So, I have here a second order differential equation. So, let me define a new variable x1 which I call as x, x1 dot I can call as x2, this is the first time derivative, x2 dot. So, if I look at here, x2 dot is essentially x1 dot is x double dot. So, if I substitute for x double dot from here, what I get is x2 dot is something like this. Okay. So, I can write this in a compact form of I have x1 and x2 as my position and the velocity. I can write well this as the rate of x, which I in general will be called as x dot, with this kind of expression where I reduced or I changed or transformed a second order differential equation into two first order differential equation. How does this look like? Well, this looks like on the left hand side I have x dot, the evolution or the rate of the states. On the right hand side I have a constant matrix which I call as the system matrix, and then the state vector here, right. So, this is a good looking structure here, right. So, which is also the first building block of any state space representation of a linear system. Okay. So, x dot equal to a x, right, where x are the states, or states are again the variables which are of interest to me. We will elaborate on this a little later, but in this case what am I interested in is the position and the velocity of the evolution of the position and the velocity. Okay. So, if I look at what does this system tell me? So, if I subject the system to a certain initial condition, well, I can see that the system will eventually go to rest because there is no external force acting on the system, and also because there is damping in the system. So, any initial condition physically it would mean that you start with a certain kinetic energy, certain potential energy, the energy will dissipate and eventually you will reach to a state of zero energy. And that is what happens even when you switch off a fan, right. So, there is no external input. So, eventually your system will come to rest, it will dissipate all the energy in terms of heat or whatever. Okay. So, these are like the typical evolution of the position and the velocity in an underdamped case. So, what is in physics literature also represented as the phase portrait is I am just looking at the evolution of the state variables with each other. So, here, so this is my position x1, the velocity x2, and then so any initial condition will actually go to the origin. You start from here, you start from here, you start from here. This is also typically referred to as the phase portrait. So, and additionally, if there is no, if d equal to 0, then I will just see some kind of concentric circles here, circle here, and so on. Okay, we will see the approximations of this, the evolution of this a little later. And similarly, if there is no damping, the position and the velocity will just be oscillating around this, around the equilibrium, like a typical oscillator circuit, or a simple pendulum which will keep on oscillating if there is no dissipation. If there is dissipation, you will just see that it will stabilize or just come to rest at the equilibrium position, which is the position of say zero kinetic energy, like and zero angle, so to speak. Okay. And then you have categorization, if you remember something from the basic undergrad course of critically damped systems and over damped system. Critically damped system will have a phase portrait which looks like this, and similarly for all initial conditions it will just follow a path in this way, right. So this phase portrait will give me a general behavior for all initial conditions. Over damped case will have a slightly slower response depending on how over damped the system at hand is, right. So, again the phase portraits will tell me things related to all initial conditions. Okay. So, again there is nothing new here that you do not know, but the aim of this is to introduce you to a new abstraction in terms of x dot equal to Ax. Earlier we called it, gave it the name of a certain transfer function, but here we will talk mostly in the time domain instead of the Laplacian domain. We will see how they interrelate to each other, the Laplacian domain and the state space domain. Another thing is to look at of how the evolution of states happens in terms of what we called as a vector field. who have done a course in electromagnetics would remember this from the field theory, right. So, just plot the vector field, I can just guess what its divergence, curl and things like that are. So, understanding phase space will be a bit important for us towards when we learn about stability and related concepts. So, we will touch upon all this very slowly. So, I am just kind of scratching the surface here, right, just introducing you to tools that we might be using in the later part of the course. So, you might just want to play around with phase portraits. You can also do this for nonlinear systems, and they will get a little more exciting too. Okay. So, what about say a force system, right. So, if I just look at a typical electric circuit, okay, let me just draw it here quickly. So, I have a V, R, L and a certain C, okay, and generating some current I L. Let me call this R, L, C and the voltage across here be V C. Okay. So, I do not need to teach you the first two equations, right. These are the basic, so this is the comes from the basic definition of the capacitor, again in the linear sense, right. So, all here so far will be linear, and then V, this comes from the Kirchhoff's voltage law. Okay. I can also write this in the previous kind of abstraction. So, I define my states as the voltage across the capacitor and the current through the inductor here, and the rate of these states, again x dot, would just take this form, right. So, I have x dot equal to A, again this A is always a constant matrix when I am talking of linear systems or linear time invariant systems or the kind of systems that we dealt with like so far. An extra thing here we see is that I have something here, that is because essentially because it is a force system. Earlier I just had the right hand side to be 0. So, here I have the external voltage, you can call it the control input or whatever. So, I have input matrix B and the control input U. So, here it's just a single input, but you can also have systems which will have more than one input. Again, we will deal with those as and when they come, but this will in general be a structure of it, a system with input. So, I look at x dot is A is as usual the system matrix, x is the state vector, B is now the input matrix and a certain input U. Okay. And now we know how a certain RLC circuit behaves to an external signal, right. So, if I just look at an impulse, that will be its natural response, so everything will go to 0 because it will all dissipate. This is as good as an unforced system in the previous case subject to certain initial conditions. So, the current will go to 0, current across the inductor or in the circuit will go to 0, similarly with the voltage across the capacitor. Step response, well it's a little interesting that you will have the current goes to 0 and the voltage builds up to a steady state value of 1 volt. This is like a unit step. Okay. Okay, how this happens, why this happens, a bit of that we would have done in maybe in an earlier control course or a networks course, but to write it in how to derive it from a general expression of a state space representation, that we will learn through this course of how do we make use of this A and B to arrive at these kind of expressions. Again, we will reserve all those for later. We are just looking at building up some of the arguments leading to a general theory. Okay. So, I also know that a good or a typical behavior of linear systems is if the input is sinusoidal, the output is also sinusoidal. What I do, much of this we did while we were doing the frequency response, Bode plots and Nyquist plots and things like that. So, this also we know, right, that the input to a sinusoidal signal, the output will be a sinusoid signal with a little change in magnitude and phase, and that will depend on my parameters R, L and C of the circuit. Okay. So, this was all about linear time invariant systems which I could write in this form x dot equal to A x plus B. This is all continuous time, right. So, the dVc by dt, dIL by dt, all signals that are continuous in time. Lot of times we also talk of discrete systems. So, if these were ordinary differential equations, we also know a bit about difference equations. So, let's talk of a simple example here. Okay, in our earlier control course we had done this in the continuous case, but we will just have a discrete equivalent of that. So, again this also comes from physics, right. So, physicists have spent a lot of time doing the predator prey models. They are also referred to as the Lotka-Volterra models, and there will be a bunch of literature on that from different domains, computational domains, linearizations, from the Hamiltonian mechanics point of view, that it is a bi-Hamiltonian system and so on. Okay, that is not the point of interest. So, let us see of what kind of models which we can evolve from this. So, the model is kind of pretty simple, or the problem is pretty simple, or we are actually working at a very simple version of it. So, I have say a pond, and I say I have some kind of small fish who feed on some weeds here, and okay, now I just want to see the evolution of this fish. So, when I say evolution, I just want to see, well, how do these fish evolve with respect to certain initial condition. So, all the models of interest, you start building with some assumptions and then slowly relax those assumptions. So, first assumption I can make here is that, well, if that this fish, they have lot of food to eat, that the resources are infinite and they almost never die. Okay. So, what would I expect even before I write down an equation, that there are say some initial conditions, say some say 1000 fish in a pond, they multiply, they have infinite resources. So, I will expect them to grow to infinity. Okay. What does that mathematically mean? That I can write this as a model, that so if I say take a difference, so this k here would be my time instant or its sampling instant, if I call in terms of the signals perspective. So, the difference of the number of fish at time k and at time k plus 1, it will always be increasing, right, because I know that they do not die naturally and they have infinite resources to feed on. So, this will be in some proportion to the number of fish at the kth instant. The multiplicity will, or the multiplying of the population will depend on the initial condition which I start at. T equal to 0 if I have 1000, t equal to 1 I may have 1002 and so on. So, if I am looking at what will happen at k plus 1, it will largely depend on what is the condition at some time instant k. Okay, and this is some proportionality constant which will depend on well, how much is or is the food constant, or it keeps on going or coming. So, my expansion will depend also on maybe if there is a lot of food sometime, maybe the food shrinks a bit and so on. But again, since I am assuming that it's infinite, I just say that, well, this is some proportionality constant. Okay, so let us say another situation where I have another pond where they have like a lot of big fish, a lot of them, okay, but they have nothing to feed on. So, what would I expect, and I also assume that, well, if they have nothing to feed on, that they will eventually die. So, what would I expect, that after a certain time instant, could be a year depending on the population, could be 2 years or so on, that the number of big fish will eventually come to 0. Okay. So, if I look at, compare the number of big fish at an instant k and compare it with k plus 1, I would imagine that it will see a decrease in population, right. So, well, this, and the decrease will depend on what was the population at time k and some proportionality constant which will define the rate of the decay. Okay. Here in the first case it always increases, second case it always decreases. Okay. Now, this is how we build model based on what our intuition says. Intuition will say that the population here will rise, will go unbounded, or in mathematics what we call it will go to infinity. Here the population will cease to be 0, and the species might become extinct, so to speak. Okay, interesting things will happen if I merge these two, that maybe make a pond where there are big guys, there are smaller guys, there is some food for the smaller guys, and the big guys feed on the smaller guys. So, the big fish feed on the smaller fish. Okay, now interesting things happen, right. So, what will you expect to happen is that these guys, the small fish population was increasing all the time, Okay. So, now when there is the big fish feeding on them, you will see a certain decrease in population, right. So, therefore, I put this C here, and okay, all these constants here are greater than 0, by the way. So, you will see that okay, the population increases when they are by themselves. When they are interacting with bigger fish, the population decreases, that is captured by this term, and the rate of decrease of population will depend on how frequently they interact with each other, and then a certain decay term also there. Similarly, what will happen to the big fish when I have small fish? Well, these guys will have something to feed on, so I will expect them to grow, right, and then the growth again will depend on how frequently they interact with each other, and of course some proportionality constant, right. So, okay, so this is, I cannot write it as any linear system here, right, because you see some kind of non-linearity here, right, the interaction term between S and B. So, I cannot write it as a certain say the discrete version of x dot equal to Ax plus x dot equal to Ax would be this one, xk plus 1 is A times xk. This is essentially the discrete version of x dot equal to Ax. Okay, I cannot write it because it is some non-linearity in this. However, what do I, how, if I just start with an initial condition, what would I expect? Would I expect say initial condition not saying that there are 2 small fish and say 2000 big fish, then I know that within that the entire model will again collapse to 0, because the 2 small fish will be eaten almost immediately, and then the big fish will have nothing to eat and everything goes to 0. Also the contrary, right. So, if I have maybe a lot of small fish, say 10,000, and just 2 big fish, then the opposite kind might happen, that one of the species might actually go to infinity and so on. Okay. So, assuming those kind of extreme conditions are excluded, okay, what do we expect, or that the behavior of the small fish and big fish to happen? Of course, one is that if you start with an equilibrium position, then they will always be like that, right. So, I just so equilibrium is when Sk is Sk plus 1, Bk is Bk plus 1, then I will get certain conditions for Sk and Bk, right, that will depend on the constants A, C, B and D. Okay, we will not derive that, that's pretty straightforward here. So, if I start at that initial condition, the population will be similar throughout, no matter what happens with the growth and decay, right. They will still follow the same pattern, but they will just be constant forever. Little around that equilibrium point, say I just say perturb it a little bit. So, what will happen is the following, right. So, at some point of time you see, well, there will be an increase in the number of small fish, so the big fish will have more to feed on, that will decrease in some way the population of the small fish and so on. So, what we see is that the populations have some kind of an oscillatory behavior. So, if I just plot it for say population in thousands on the x axis, and say over a period of say 90 or 100 years, I see some pattern like this. Okay, this you can just look at like at the phase space of these systems and so on. Okay, so we started off with linear time invariant systems. So, this is a discrete nonlinear system. Okay, we will formalize that a little later, which will give some kind of an oscillatory behavior. And in the first 2 models here, I actually knew these equations from physics, or as what they call also as first principles, right. So, I know the Kirchhoff's voltage laws, I know the current laws, Newton made my life easy to model a mass spring transfer system and so on, but here the models are, well, nobody gave me a model here, right. So, I am just building models as an abstraction to what I would observe, and I can maybe validate those models, right. So, so here it's partly by intuition and partly by observation also, and partly by what I would know about a bit of evolution theory. So, that concludes the first part of this lecture, and we will do some more examples in the next part. Thank you.